Welcome student. Welcome student. Today we are going to see the chapter number 8 of the physics, that is the electrostatics. Now see, in this chapter we are going to see the electrostatics chapter. In this we are going to see what happens when the electric charge at a rest position. Because of this rest position, this charge gives the electric intensity in its surrounding space. Okay, we know this Gauss law. In 11th standard we were familiar with the Gauss law. That is, the flux of the net electric field through a closed surface equals the net charge enclosed by the surface divided by epsilon naught. That is, equation 5 is equal to Q upon epsilon naught, which is also equal to integration over a closed surface. This indicates the closed surface, okay, then A bar into ds, where this E bar is the electric field intensity and the ds is nothing but the area, where this Q is the total charge. This Q is the total charge within the surface, that is the Gauss law, is applicable to any closed surface or of regular or irregular shape. This is equation number 1. This equation number is also called as the equation A, because in next we are going to see how we obtain the electric intensity because of the different surfaces, and for that we are going to see the common steps to obtain the electric intensity at the different points. Now see, the common steps involved in calculating electric field intensity by using Gauss theorem. First, describe the charge distribution, linear, surface or volume. That means according to the given shape or surface, you have to distribute or describe the charge distribution. Then obtain the flux by Gauss theorem, which we have learned in earlier slide, that is the equation number A. Okay, then visualize a Gaussian surface and justify it. Then with the electric field intensity E as unknown, obtain the electric flux by calculation using geometry of the structure and symmetry of the Gaussian surface. That is the equation number B. This equation number B is nothing, the equation which is obtained with the symmetry of the surface, and that equation number B. Equation number E with the help of Gauss law, and equation number B is with the help of the surface geometry. Okay, then you have to equate this equation number A and equation number B. With equating this equation, we have to simplify this equation for the electric intensity. In this way, we can find out the electric intensity. On the basis of these common steps involved in calculating electric field intensity, by using the Gauss theorem, we are going to find out the electric intensity from the different surfaces, and this is nothing but the applications of the Gauss law. Now let's move towards the next topic of this chapter, that is the application of the Gauss law. In application of the Gauss law, first we are going to see, that is the application of Gauss law, that is electric field intensity due to uniformly charged spherical surface, or which is also called as the holosphere. Now in this case, see, first of all, this diagram, you have to concentrate on this diagram. If you understand this concept, then easily you can find out the electric intensity. Okay, this is the surface. Here I show inner surface, that is the inner sphere, where the radius is r. Consider a sphere of radius r with its center O charged to a uniform charge density. We know that this charge density sigma is equal to charge per area. Therefore, this is coulomb and this is the meter square. This is the units placed in a dielectric medium of permittivity epsilon. Okay, therefore epsilon is equal to, we know that is with the help of dielectric constant, we have the equation epsilon is equal to epsilon naught into k. Therefore, the total charge on the sphere, therefore rearranging the term, we got Q is equal to sigma into 4 pi r square. Once again, see how this equation we obtain. We obtain this equation with the help of this sigma. Sigma is equal to, that is the charge density is equal to charge per unit area. So for charge, we have made this equation with the help of this charge density. Now therefore by Gauss theorem, again we have, this is the, with the help of common steps or considering the common step, we got the first equation which is given by the Gauss theorem, that is the flux is phi is equal to q upon epsilon naught, where the k is constant. If the surface or the area which is we consider this air or vacuum, at that situation this k is equal to 1, where q is the total charge inside the closed surface. This is the equation which we got with the help of this Gauss theorem, that is phi is equal to q upon epsilon naught k. Finally we got the equation q upon epsilon naught. Okay, this is equation number 1. Next, therefore, again, now we are going to move towards to obtain the equation B, and then the next step is we have to equate these two equations, that is the equation A which we obtain with the help of the Gauss theorem, and the equation B which we obtain considering the spherical, the symmetry of this surface. Okay, imagine a concentric Gaussian surface of radius r passing through P. Now we have to consider this surface. For that we have considered the point P, which is at a distance r from this charged surface which is having the radius capital R. From this charged sphere or hollow sphere, where is the point P, which is at a distance r. The aim of is that we are going to find out the electric intensity at the point P, which is at a distance r, and for that we are going to make the equation B. Okay, now let us consider the ds area be the small area around the point P on the Gaussian surface. Now this imaginary circle which we draw for our consideration or the for understanding level, we have to draw this next sphere having the radius r. Why radius r? Because we are considering the point P at a distance r. Okay, the electric field intensity at a point P at a distance r from the center of the charged sphere. Therefore, the flux, we are going to see the symmetry of this sphere. So, d phi is equal to E bar into ds. Now, this ds is nothing the small part of the circumference of this sphere. Okay, therefore again equation becomes, this is the scalar product, therefore E ds cos theta. Again this theta here is equal to 0, therefore the angle between the E bar and this sphere, this ds is 0, so cos 0 is equal to 1, and finally we got the equation E into ds. The total electric flux through the Gaussian surface. Now this is for ds, okay, this is for ds. Therefore, this is for ds, so that we have the equation, that is the E into ds, that is the integration over this ds is equal to E into 4 pi r square. From equation 1 and equation 2, we got the equation, that is the equation, therefore for finding equation, therefore, for finding, we got this equation. This is the small part of the circle. Therefore, circumference, we get q upon epsilon naught. This is the equation number A, and E into 4 pi r square. Therefore, E is equal to q into 4 pi epsilon naught r square. We make the equation for this E, and this is nothing but the equation, that is the E is equal to q. Therefore, q is equal to, that sigma into 4 pi r square, 4 pi epsilon naught r square. This 4 pi get cancelled, and therefore q is equal to sigma into 4 pi r square. Therefore, E is equal to, finally we got the equation, that is E is equal to sigma r square upon epsilon naught r square. Now see the case number 1. If point P lies on the surface of the charged sphere, suppose this r, instead of this r, the distance of this point P is nothing on this surface, therefore the radius, this r become or equal to capital R. Therefore E is equal to sigma divided by epsilon naught. Therefore, case number 2, and equation become r square get cancelled, therefore sigma upon epsilon naught. Case number 2, if point P lies inside the sphere, then again, since the There are no charges, therefore inside sigma is equal to 0 and therefore E is equal to 0. These are the cases belonging to this first application of the Gauss law. Now next application of this Gauss law, that is the electric field intensity due to an infinitely long straight charged wire. Therefore, consider a uniformly charged wire of infinite length having a constant linear charge density lambda. Charge per unit length. Here this linear charge density, that is the length. It is related length. Therefore, charge per unit length kept in a medium of permittivity epsilon is equal to epsilon naught k. Then again by Gauss theorem, the net flux through a closed surface, that is the phi, is equal to q upon epsilon naught k, where q divided by epsilon. Therefore, imagine a coaxial Gaussian cylinder of length L and radius r closed at each end by plane caps normal to the axis passing through the point P. Consider a very small area ds at the point P on the Gaussian surface. Like as a first, we have to consider here this is the long conducting wire. Okay, and because of this charge long conducting wire, we are going to find out the electric field at the point R, that is where this point P, we are going to find out the electric intensity. See, this looks like a cylinder. So again we have, with the geometry, we make this Gaussian cylinder, and with the help of this we are going to find out the equation number A and equation number B, and again we equate these two equations and finally we got the electric intensity. Therefore, to find the electric intensity at P at a distance r from the charged wire flux d phi through the area ds. d phi is equal to E bar into ds, which is equal to E ds cos theta. Okay, therefore E ds. Therefore theta is equal to 0. Again, this angle between this E and ds is equal to 0, so this cos theta is equal to 0. Therefore E into ds. Total electric flux through the Gaussian surface phi. Again we are going to take the integration. That means we are going to find out the flux throughout this Gaussian surface. For that purpose we are going to take the integration. Therefore integration over this E bar into ds, therefore which is equal to nothing but again the area, that is the again total area, that is the cylinder. Therefore it is 2 pi rl. Again equating equation number 1 and 2. Therefore from equation number 1 and 2, this q upon epsilon naught, which is equal to E 2 pi rl. Again this q divided by 2 pi rl epsilon naught which is equal to E. Therefore again rearranging the equation, we got this E is equal to q 2 pi rl epsilon naught. Okay, again we have this equation, that is the q is equal to, here this q is equal to, that is lambda is equal to q upon L. Therefore q is equal to lambda into L. Therefore this E is equal to, again we got putting this value of this q in terms of this lambda, we got the equation E is equal to lambda divided by 2 pi rl epsilon naught. Therefore E is equal to, finally we got the equation, that is E is equal to this lambda divided by 2 pi rl epsilon naught r, and this is the equation for this. Now the next application is that the electric field due to a charge in finite plane sheet. Now in front of you, this is the diagram of this plane sheet. It looks like, you can also imagine your notebook cover like this, that is the plane sheet. Okay, consider a Gaussian surface around P in the form of a cylinder having cross-sectional area A and length 2r, with its axis perpendicular to the plane sheet. The plane sheet passes through the middle of the length of the cylinder, such that the ends of the cylinder called end caps P and P dash are equidistant at a distance r from the plane sheet. So this R and R, these are these 2 points we are taking here, P and P dash. which is having the equal distance from this plane sheet, and we are going to find out the electric intensity of these 2 points. You can say that left side and right side. Okay, again in this concept we are again going to see, that is again we are going to obtain the two equations, that is the equation number A and equation number B. One is with the help of Gauss theorem and second one is with the help of this geometry of this diagram. Therefore, total flux through the closed surface is given by, therefore phi is equal to integration E dsP. That is for this P, and next one is the integration over EDS for the P dash. Again this theta is equal to 0. Therefore cos theta is equal to 1. And for that this is surface. ds is for ds integration over this ds. Nothing but the total area. And we are going to consider here this total area is equal to capital A. Therefore phi is equal to EA plus EA, which is equal to phi is equal to 2EA. This is the equation number 1. Or you can say according to the common steps, this equation number B. Again, sigma is the surface charge density. With the help of this, we can say that sigma is equal to Q upon A. Therefore, for the equation for this charge, Q is equal to sigma into A. Putting this value in equation of the basic Gauss law, therefore we got phi is equal to sigma into A instead of this Q, there divided by epsilon. This is the equation number A. Equating this equation 1 and 2, we got therefore 2A is equal to QA epsilon naught is equal to, that is therefore finally E is equal to sigma divided by 2 epsilon naught. And this is the third application of the Gauss theorem. These are the applications of the Gauss theorem. That means with the help of this Gauss theorem we can obtain the electric intensity at a given point, equating or considering the common steps which is given. Now next, what is the difference between this electric potential and potential energy? Therefore, electrostatic potential energy is nothing but the work against the electrostatic forces to achieve a certain configuration of a charges in given system. This electrostatic potential, that means we are going to change the initial position of that particle, that is that charge. First, electrostatic potential is nothing but it's the work against electrostatic force. We know that there are the electrostatic forces between the two charges which is situated at a finite distance from each other. According to the Coulomb's law, there are the force of attraction or the force of repulsion according to the magnitude or the positive negative on that charges. These forces to achieve a certain configuration of the charges in a given system. Now consider a positive charge Q fixed at some point in space. For bringing any positive charge to close it, then we have to do some work, and that work is very necessary. This work is equal to change in the potential energy. That means we are going to change the initial position of that substance, so that we are saying there is a change in its potential energy of their system. Thus, the work done against electrostatic force, which is equal to increase in the potential energy of the system. Again, we know that the basic concept of the work done is nothing that the force into displacement, and which is equal to work done is nothing but the change in the potential. Suppose U is the initial potential, and because of this work done, there is a change in its state, and so that there is a change in its potential energy. And so this F bar into dr, which is that is the work done, which is equal to this du. Du is nothing but the increase in the potential energy. When the charge is displaced through dr, and F bar is the force exerted on the charge. This is nothing but the electric potential and the potential energy. Now the next, which is very important concept, which is related to this potential energy and electrostatic potential, that is the expression for the potential energy. Now see in diagram, we are going to bring this is the positive Q charge, okay, and because of this charge there is the electric field intensity in the surrounding space. Suppose A is the another charge which is at a distance r1 from this positive charge. And now we have to displace this charge to a small distance up to this dr and finally up to b against the force of attraction, that is the electrostatic force. Therefore, let us consider electrostatic field due to a source charge, that is the positively q placed at the origin O. Let us a small charge, this is q naught, be brought from A to B. This A to B were moved against this electrostatic force at respective distances r1 and r2 from O against the repulsive force on it. Why repulsive? This is positive, this one is also positive, so the force of attraction or there is the force is force of repulsion. Again, this Fe in displacing this charge Q naught through a small displacement, that is dr, appears as an increase in the potential energy of the system. Therefore, du is equal to Fe, that is the force into dr. Why this is minus sign? Because this work done, that is the against or the force, that is the negative sign appears because the displacement dr is against the electrostatic force Fe. Now see, for the displacement of the charge from the initial position A to final position B, the change in the potential energy delta U can be obtained by integrating du. Therefore, delta U is equal to integration. We are bringing this charge from R1 to R2. Therefore, du is equal to, that is R1 to R2. That is du is nothing but the work done. Therefore, Fe into dr. The electrostatic force, that is the Coulomb force between the two charges, that we can also say that is the repulsive force, separated by a distance. Again, we know the value of this force, that is the 1 upon 4 pi epsilon naught capital Q, then Q naught R square, and this is nothing but the R is nothing but the distance between the two charges. Using the Coulomb's law, we got this F. For a system of 2-point charges, delta U is equal to R1 to R2 du. Therefore, R1 to R2, again du is equal to Fe into dr, that is the work done. Again, equating this equation, this delta U is equal to R1 to R2, again putting the value of this Fe, here this is equation becomes like this, that is the delta U is equal to R1 to R2 integration, or therefore minus 1 upon 4 pi epsilon naught and Q naught Q naught R square into unit vector R bar, which is indicate the direction. Okay. Therefore, delta U is equal to R1 to R2 minus 1 upon 4 pi epsilon naught into Q naught. Therefore, again with the formula of the integration, we got this 1 upon R square dr. Solving this term, finally we got this delta U is equal to 1 upon 4 pi epsilon naught into capital Q, that is the first charge, and then next charge Q naught in bracket the upper limit minus lower limit, therefore R2 minus 1 upon R2 minus 1 upon R1, and the change in the potential energy is equal to the work done. Therefore, this work done, what is this WAB work done to bring in this charge from A to B against the electrostatic force is given, that is delta U is equal to 1 upon 4 pi epsilon naught, and then this Q naught 1 upon R2 square minus 1 upon R1. Thus, the potential energy U of the system of 2-point charges Q1 and Q2 separated by R can be obtained from the above equation. That means to obtain the equation, we got the formula for the work done, and simultaneously we got that is the potential energy. Therefore, using R1 is equal to infinity and R2 is equal to R, it is given by this work done, that is the W is equal to, that is this W is equal to delta U. Again, suppose we are having the value this R1, that means we are bringing this charge from infinity to R. Therefore, this R1 becomes infinity. The value of R2 is equal to R. Putting this value in this equation, we got 1 upon 4 pi epsilon naught into Q1 Q2 1 upon R, because here we take this value, that is the R2 is equal to R. So 1 upon R minus 1 upon infinity. 1 upon infinity is equal to 0. Therefore, finally, we got the equation U, that is this work done is equal to, for two charge system, that is 1 upon 4 pi epsilon naught into Q1 Q2 and 1 upon R. This is nothing but the equation or expression for the potential energy. Today we stop here, and in next session we are going to see, that is the units of the potential energy.